Alright, so we got the initial length of the spring, and then we started hanging different weights on the spring and then measuring how much the length of the spring changed in order to get the delta X. And then we converted all that into direct units of newtons and of meters. And after that, we got all of our points and we graphed it onto there, that equation.
And
then from that, it gave us a K of around 3.68736
newtons per meter.
Yeah.
And that's because of our slope of the line.
Also, the X part of the graph is the displacement of it from the initial position, and the Y part is the Fs, which is also equal to Fg.
It's equal to Fg because they're at equilibrium in each position with the new mass.
Okay, so this is our spring system that we created.
A little iffy with the tape, but that was to balance it because these bars aren't perfect or whatever. But you hang a mass, it's still going to be like relatively balanced out. So 6 springs. Okay, so we have the diagram on paper now, right? And we know that each spring has the same K constant. So we combined the parallel springs first to get the K top, K mid, and K bottom as we labeled it, right? And with that, we found the KEQ by combining the springs in the series using the formula over here. And doing that, we found 6/11K is equal to KEQ, which we converted over here to 2.011 newtons per meter as the KEQ. And we did that to find the delta X net in order to verify our data later on. But since we're finding the individual extensions of each spring, we'll work starting from the bottom spring. And we know that the weight is going to be distributed evenly throughout all the springs. Alright, let's start with how we got our formulas to find the displacement of each spring. So you know by Hooke's law, Fs is equal to negative Kx. But to isolate for x, I'm going to be dividing by negative k. So this goes away. But however, since I'm extending the spring down, right, the negative from here is going to cancel out with that negative, which is why I just removed that. So I got that x is equal to Fs over k. We know that a spring in equilibrium doesn't move, which means that the Fg force has to cancel out the Fs force. With that logic, we can use a theoretical weight of 50 grams and calculate the Fs from that, because 50 grams, when converted to kilograms and multiplied by gravity, is going to equal 0.449 newtons, which is same magnitude as the Fs, because at equilibrium they don't move. Okay, let's start with delta x bottom. So using the formula I explained earlier, delta x bottom is equal to Fs over k bot. And k bot is the K constant of this bottom spring, right? But since it's only one spring, then k bot is equal to K. So using that for the math, 0.49 newtons is going to be equal to Fs, which I declared earlier. And then k bot is the same as the K we calculated, which is going to be 3.68736. And using that math, we get 0.133 meters as the calculated theoretical extension. And then as we calculated, the actual extension is 0.11 meters. Alright, let's move to delta x mid now. Same formula, delta x mid is equal to Fs over k mid. However, this time it's 2k. This is because there's two springs in a parallel system, which is why k plus k equals 2k equals k mid. Using that math, we have the same Fs because the Fs is distributed evenly between everything. And then we have 2 times the k we calculated earlier, which gets us 0.066 meters as the theoretical extension, and the actual extension as 0.07 meters, which is pretty close. Okay, now let's go to the top springs delta x. Delta x top equals Fs over k top, which is 3k because now it's 3 springs in the parallel system. K plus k plus k equals 3k. Anyways, Fs is the same as we calculated before, and now it's 3 times k, which is right there, 3 times k. And that equals 0.044 meters. And when measured, the actual delta x is 0.06 meters, which is a little off, but it's theoretical versus actual. Now let's look at our actuals, which we measured. And our actual xnet is 0.24. They all add up equally. And now let's look at our theoreticals over here. And when added up, they equal 0.244 meters, which is actually really close, which is pretty good experiment.
Yeah. So yeah, that's our spring system.